And that's what we're digging into today. We're looking at the industry standard, the Mark III containment system.
But just to be clear for you listening, we're not just doing a spec sheet review here. We've pulled together a stack of technical reports on failure mechanisms, fluid dynamics, and risk assessments.
Right.
Our mission is to figure out exactly how this thermos works, but more importantly, how it fails. We're hunting for leaks in the mysterious interbarrier space.
Which really does sound like something from a sci-fi movie, the interbarrier space.
It does. So buckle up. We're going to understand why something called sloshing is an engineer's worst nightmare and look at the high-stakes detective work needed to spot a tiny leak before it becomes a disaster.
And to do that, we have to start with the design, because I think a lot of people assume an LNG tank is just a big cylinder dropped into the hold of a ship.
That's exactly how I pictured it, like a battery and a flashlight.
But the Mark III system, it isn't a separate tank. It is the lining of the ship. It's a membrane system. If you were standing inside an empty one, you'd be struck by the walls. They don't look normal.
Okay, let's unpack that. I'm standing inside the tank. What am I looking at?
You're looking at the primary membrane, the first line of defense. It's made of 304L stainless steel, but it's not a flat sheet. If it were flat, it would be ripped apart the second the LNG hit it.
Because of the temperature change.
Exactly, thermal contraction. When you cool steel from room temperature down to minus 163 Celsius, it has to shrink. Physics demands it. If you just welded a flat sheet to the wall, that tension would snap the welds.
So how do they get around that?
It's a brilliant solution. The steel is corrugated.
Corrugated, like cardboard.
A bit fancier, but yes, that's the principle. It looks like a massive, shiny waffle pattern covering everything.
I love that description. A steel waffle. But functionally, what does that pattern do?
Think of an accordion. The corrugations give the metal extra material to sort of pay out. When the temperature drops and the metal shrinks, the waffle folds just flatten out a tiny bit.
So it allows the metal to move without stressing the material.
Precisely. It decouples the thermal movement from the structure. It gives the steel permission to move.
That's elegant. So that's the face, the part touching the gas. But a thin sheet of steel doesn't stop the cold, does it?
No, steel is a terrible insulator. It conducts heat really well. So behind the waffle is the muscle, the insulation panels. Thick blocks of reinforced polyurethane foam, or RPUF, backed with plywood.
Wait, plywood. We're using wood on this high-tech spaceship of the sea.
It surprises everyone, but plywood is actually fantastic at cryogenic temperatures. It doesn't shatter like some plastics would. The insulation layer does two things. It keeps the cold in, obviously, and it also absorbs the kinetic energy of the cargo.
Okay, so a steel waffle face and foam and plywood muscle. Well, you mentioned the interbarrier space. Where does that fit in?
This is where the engineering gets really paranoid, in a good way. Behind that insulation, there's a third layer, the secondary membrane. They call it the triplex.
Triplex. What's it made of?
It's a composite sandwich, a layer of aluminum foil between glass cloth and a rigid composite. This is your safety net. If the primary steel waffle fails, if it cracks, the triplex is designed to catch the liquid.
And the space between the primary steel and this triplex safety net.
That's the interbarrier space, the IDS. It's a tiny gap filled with nitrogen gas.
Why nitrogen? Why not just air?
Air has oxygen and moisture. Oxygen plus natural gas is a bad combination.
Right, an explosion risk.
And moisture would freeze instantly. Nitrogen is inert. It creates this controlled, dead atmosphere as a tracer. If you're monitoring that space and suddenly you detect methane,
You know the primary barrier is breached.
you know instantly. The IBS is the demilitarized zone. Nothing should be in there but nitrogen. It's the void that tells the truth.
So the system has a backup plan built right in. That sounds robust. But we know failures happen. And the biggest villain in this story seems to have a deceptively silly name.
Sloshing.
Right. It sounds like me walking too fast with my tea.
Not quite. We're talking about tens of thousands of tons of liquid.
Yeah.
When that moves, it hits the tank walls with massive force.
And the reports highlight a specific danger zone. It's not when the tank is full, is it?
No, and that's the counterintuitive part. When the tank is full, the liquid is constrained. It moves with the ship, almost like a solid block. The roof keeps it steady.
And when it's almost empty, there's not enough mass to do damage.
Exactly. The danger zone is partial filling, usually between 10 and 70% of capacity.
Why is that middle ground so dangerous?
Because the liquid has room to move out of sync with the ship. It's all about resonance.
Resonance. Like pushing a child on a swing.
Perfect analogy. If you push at the right time, the resonant frequency, it goes higher and higher. The liquid in the tank has a natural frequency, around zero point 0.6 to zero point 0.8 hertz. When the ship's motion matches that, the waves inside the tank amplify, they get bigger and bigger.
I saw some staggering numbers on the pressure, these hydrodynamic impact pressures.
Yes. We see peaks of 10 to 20 bar, or sometimes cited as up to 20 kilopascals. But forget the units. Think about a wave hitting a wall with 10 to 20 times atmospheric pressure repeatedly, every few seconds.
It's a hammer.
It is a hydraulic hammer, and this brings up a concept called hydroelastic coupling.
Which sounds incredibly complicated.
It is. It's the interaction between the fluid's motion and the wall's elasticity. See, the wall isn't perfectly rigid. Remember the foam and plywood? It gives a little...
So the wall bounces back.
To a degree. And if that interaction isn't modeled perfectly, you can underestimate the damage. The wall can effectively punch back into the wave, amplifying the shock.
So you have this violent liquid hammering the walls. And we can't forget the cold factor. How does being at negative 163 degrees C change how these materials handle that beating?
This is the double-edged sword of cryogenics. At those temperatures, 304L stainless steel actually gets stronger. Its yield strength goes up.
That sounds good. We want strong steel.
It sounds good, but there's a trade-off. It becomes less tough.
Amy.
Toughness is the ability to absorb energy without fracturing. The steel becomes more brittle. It's more likely to crack than to bend if it gets hit hard.
Like the difference between a rubber tire and a ceramic plate.
Great analogy. And it's not just the steel. The plywood and foam are contracting too, but, and this is the key, they contract at different rates.
The materials are fighting each other.
They are. The mismatch creates massive tension. The source material notes that thermal contraction alone can cause strains up to 0.5%.
That sounds small, 0.5%.
In engineering terms, for a structure this big, that is huge. It means the materials are constantly pulling at each other just because of the temperature before the sloshing even starts.
Okay, let's set the scene for the crime. You have a material that's already stressed, brittle from the cold, and now you start hitting it with a liquid sledgehammer.
That is the recipe for failure.
So how does the failure actually happen? It's not one giant wave punching a hole in the ship.
Rarely. It's not, almost always fatigue. Not one hit, but millions of cycles. Over a 20-year life, a ship might see 10,000 to 100,000 of these big sloshing impacts.
That's a lot of abuse. Where does the armor crack first?
At the weak points where things connect, you have the mastic areas, the resin glue connecting the insulation panels. You have bridge pads, which are structural supports.
Why are those a problem?
Because they're hard points. You have soft foam next to a hard pad. A wave hits, the foam compresses, but the pad doesn't. That creates a stress concentration right at the edge.
It shears the membrane.
Exactly. And of course, the welds in the steel waffle itself. A microcrack forms from that mix of fatigue and thermal stress. Now, at room temp, a crack might grow slowly. But remember the temperature.
The cold accelerates it.
Significantly. Cryogenic temperatures accelerate crack growth rates by 2 to 3 times. The material just doesn't have the energy to stop the crack from unzipping.
Wow. So the cold is like a supercharger for the crack.
Exactly. The crack propagates until it breaches the primary membrane. Now, LNG flows into that nitrogen-filled interbarrier space.
And that's the top event. Once the LNG is in the IBS, what's the immediate threat?
Not an explosion, not immediately. The first threat is thermal. The LNG vaporizes, cooling the insulation even further, maybe beyond its limits. It can degrade the plywood. If the leak is bad enough, liquid pools against the secondary barrier, the triplex.
And if the triplex fails?
Then the cold hits the carbon steel hull, the nightmare scenario. Carbon steel at negative 163 degrees CR is incredibly brittle. If the hull gets that cold, it can fracture. The ship could structurally fail.
The ship snaps.
The structural integrity is compromised. That's why the IBS is so critical. It's the early warning system.
Okay, the IBS is the canary in the coal mine. Let's talk detective work. How do they know a leak has happened?
It's all about monitoring the atmosphere in that gap. Ships have gas detection sensors that constantly sniff the nitrogen in the IBS. If they detect methane, an alarm goes off.
Is they just sniffing for gas?
They also monitor pressure. If liquid LNG leaks in, it vaporizes. Liquid expands about 600 times its volume when it turns to gas. So a sudden pressure spike in the IBS is a huge red flag.
But there's a catch, right? The sources mentioned a lag time.
Significant lag. The IBS is a maze of insulation and supports. A small leak in a corner might take time for the gas to diffuse and reach a sensor.
So a leak could be active for minutes.
Potentially longer. Before an alarm triggers, it's a blind spot.
So relying only on sniffing isn't enough. We need to prevent the cracks. How do engineers mitigate this sloshing monster?
Strategy 1 is physical design. You'll often see baffles inside the tanks.
Like breakwaters in a harbor.
Exactly. Or dividers in an ice cube tray. Physical barriers to break up the waves. Baffles can reduce sloshing loads by up to 50%.
It seems like a no-brainer.
It adds weight and cost, but it works. Strategy 2 is operational. Captains have strict rules on filling levels.
The danger zone we talked about.
Yes. In rough weather, you're not allowed to keep tanks at that 10% to 70% level. You either fill up to 98% or empty out.
What if you have to deliver half a load to one port and half to another?
And that is the huge challenge for the modern LNG market. It used to be point A to point B, full tank. Now ships do milk runs. That restriction is a huge logistical headache.
Which brings us to the high-tech solution, digital twins.
This is the future. It's using physics of failure models.
Break that down for us.
Instead of waiting for an alarm, they create a digital replica of the ship. They feed this model real-time data waves, weather, the ship's motion.
So the computer knows exactly how much the ship has been beat up.
Exactly. And it calculates the fatigue on every single weld in the tank based on those motions. It accumulates the damage. It can predict, hey, that weld in tank 3 is at 90% of its fatigue life. It's about to fail.
That is incredibly cool. It's moving from reactive detection to proactive prediction.
Precisely. It turns the ship's history into a maintenance schedule. They call it prognostics and health management, or PHM.
So what does this all mean for the lifespan of these ships?
Well, the triplex barrier is designed for 25 to 40 years, but, and this is a big but, studies show that heavy operation with partial filling can reduce that effective lifespan to just 20 years.
It cuts the ship's life in half. That's hundreds of millions of dollars.
Potentially. That's why risk assessment is so huge. They use methods like fault tree analysis and bow tie analysis.
I love the visual of a bow tie analysis. What is that?
Imagine a bow tie diagram. The knot in the center is the top event, our IBS leak.
Okay, the knot is the leak.
The left side of the bow tie is all the threats leading to the event. Sloshing, bad welds, human error. You put barriers on the left side to stop them.
So baffles in good welding are left side barriers.
Correct. The right side represents the consequences after the leak. Hull fracture, fire. You put barriers on the right side to mitigate the damage.
Like the triplex and the gas alarms.
Exactly. The goal is to prevent the knot from tying, but if it does, make sure the right side doesn't explode.
You mentioned human error. It always comes back to people, doesn't it?
It's the classic weak link. You can have the best digital twin, but if a welder was tired and left a tiny pore in the steel, physics will find it. Or if a captain is under pressure to meet a schedule, they might sail too fast in rough weather with a half-full tank.
Pushing the limits.
Exactly. The tech can be perfect, but if the operation is flawed, the risk skyrockets.
Looking ahead, is there new tech coming that solves these problems?
There is a lot of research into acoustic sensors.
Listening for the crack.
Yeah. Acoustic emission monitoring. When a material cracks, it releases a burst of energy, a sound wave. If you can tune sensors to hear that specific frequency, you could identify a microcrack the moment it forms.
Before the gas even leaks?
Long before, it fundamentally changes the maintenance game. I heard a crack in tank 2.
That would be a game changer.
Also, materials science is moving forward. Work on advanced composites to replace the plywood insulation.
It's still amazing to me that we rely on plywood. It works. But upgrading that just makes sense.
It really highlights the blend of old and new tech in these systems. You have advanced physics models running alongside wood and glue.
So let's bring this in for a landing. We've gone from a giant steel waffle to a microscopic crack caused by a frozen wave.
And the big takeaway for me is redundancy. The Mark III system is a marvel, not because it's unbreakable, nothing is. It's a marvel because it assumes failure is possible.
It's pessimistic engineering.
It's realistic engineering. It assumes the primary barrier might leak, so it builds an entire secondary system and a monitoring zone just for that. It's managed risk at the highest level.
It's engineering humility, admitting that nature and sloshing might win around, so you better have a backup plan.
Exactly. It's about resilience, not just strength.
But here's a final thought for you to chew on. We talked about how partial filling is the danger zone. The global energy market is changing. Ships aren't just going point A to point B anymore. They're floating trading platforms.
Which means a lot more time spent with partially filled tanks, a lot more exposure to that danger zone.
Exactly. So if we're moving toward a world where ships need to be more flexible, are our current designs robust enough? Or are we sailing into a fatigue trap that won't show up for another decade when all these ships start hitting that 20-year mark and the cracks start to show?
That is the multi-billion-dollar question, and the answer will determine the safety of the next generation of energy transport.
A fascinating look inside the hull. Thanks for diving deep with us today.
Always a pleasure to explore the engineering behind the scenes.
Until next time, keep asking questions.